Hey, this is Mr. Roark. This is the video review for Unit 4. Unit 4 dealt with gravity. So we'll look at Newton's law of gravitation. We'll talk about satellites in motion. We'll look at projectile motion, do a few equations to make sure you're caught up on all the concepts. Major things you have to be able to do for Unit 4 is projectile motion questions. So really the best way to look at this is just to do a problem. Let's say we've got a car, or in this case a bus, and let's say it's driving along and it drives off horizontally at a velocity of, let's just say 10 meters per second. We also know that the height of this cliff that it's driving off is, let's say, 30 meters. Okay? Now, because the projectile motion questions that we do are all based on this horizontal motion, it actually makes it pretty easy. If this thing takes off at some sort of angle, then we have to take into account how fast it's moving upward or downward or whatever, and it gets a little bit more complicated. You got to be able to do trigonometry to be able to do that. But because this thing gets shot off horizontally, we know two things. Number one, in the vertical axis, up and down, it's not moving. This thing in the vertical axis is moving just as if you would have dropped it. This velocity of 10 meters per second is straight sideways, straight horizontal to begin with. So that doesn't affect the vertical motion at all. So vertically, it doesn't matter if you drop an object from 30 meters or if it drives off at from 30 meters high. It's going to have the exact same motion in the vertical axis. We also know that in the horizontal axis, because we're going to expect air resistance here to be negligible, this thing should not speed up or slow down. As that bus goes flying through the air, hits the ground, the whole time that sideways velocity of 10 meters per second is going to stay with it. So when it left the top of the cliff, it was moving 10 meters per second sideways. When it hits the ground, it's moving 10 meters per second sideways. Now it is going to gain some vertical motion. It is going to end up moving faster in the vertical axis because it's speeding up as it's falling, but that's only the vertical axis. The vertical and the horizontal axis don't have anything to do with each other. And because of that, we can look at them independently. So let's put that stuff back up there. So I like to divide my paper into two sides when I'm doing these types of problems. I know I'm going to be using the position equation here because I know how tall the cliff is, and the other thing that I want to know is how far it goes. So in both of those cases, we need to use the position equation. But for the vertical axis, so I should write vertical here. The position equation, when we put it out, there's a few things that we can fill in here. First of all, we know that this thing starts at a position of 30 meters. So x0 is 30 because in the vertical axis, that the positioning here is just the height that it's at. We also know that it's going to end up at 0 meters. So that's the distance that it covers. It goes from 30 to 0. We know both of those things. In the vertical axis, we said the initial velocity is 0. Just as if you were to drop an object, when this thing comes off, it's not moving upward, it's not moving downward. So for the vertical axis, we don't put 10 in here because that's its sideways motion. In the vertical axis, its initial velocity is 0. We don't know what the time is. That's our unknown. So we need to put that in as just a variable. And I'm going to put parentheses around here just to help keep the stuff together. Okay? Now, the acceleration in the vertical axis is just the acceleration due to gravity. Whether we drop it or it goes flying off the cliff, in the vertical axis, gravity is what's pulling it down. As long as there's no significant air resistance, it's the only force. So the acceleration here would have to be 9.8. But I'm going to go ahead, because it's half the acceleration, I'm going to put in half of 9.8, which is 4.9. And then again, time is our unknown, so we're going to put our unknown variable here. At first glance, it might look like there's two unknown variables here. How are we supposed to solve that? But if we look at this case, we have 0 times t, and it doesn't really matter what the time is going to be. This part cancels out. The other thing that I would do, we're going to isolate this t over here. I would subtract 30 from each side to get it on the other side of the equals. And so then we get negative 30 equals 4.9 times t squared. And here we can see I've made a little bit of a mistake. Because the way I set up my cliff downward was towards 0, and this thing is accelerating downward, then I really need a negative sign in front of my acceleration. So my acceleration here is negative 4.9. And then from this point, we simply solve it. So the first thing to do would be to divide by negative 4.9 on each side. So I'll cancel that out, divided by negative 4.9, and we get 6.1224, round that off at that point for now, equals t squared. But we're not done. But at this point, we then have to take the square root of each side, because we have to cancel out that square. So we take the square root of t squared, that cancels that, and we get t. And then take the square root of our number, and we get 2.47 seconds, rounded to 3 significant figures. So what this tells us is that based on the vertical axis, it's going to take 2.4 seconds for this bus to fall that 30 meters. And remember, it doesn't matter how fast it's going. It could have been moving 10, we could have dropped it, it could have been moving 100 meters per second. Every single case, if it goes off horizontally, and it falls 30 meters, it will take exactly this time. We can see there's nothing about horizontal motion in here. Now, to figure out how far it goes, we need to use the position equation again. And this is where people get confused, I think. They think, oh, I've got this position equation, so I need to start filling in all this stuff that I filled in over here. But the point is, this is for the horizontal axis. These two things do not mix. You do not put anything in the horizontal axis that you put in the vertical axis equation, because the measurements are completely different. The only thing that can go between each axis is time, because it doesn't have a direction. And that's the point. We use the vertical axis to find the time, and then we'll put that up into the horizontal axis and use it to figure out how far the thing goes. So let's continue filling out our equation here. So in this case, let's start with x. X is the final position that it ends up with. That's our unknown, so we'll just leave that as our unknown. We don't know how far it goes. X sub 0 is the starting position. As far as the horizontal axis is concerned, we can call that 0, because we just want to know how far this bus is going to go. So we'll make that 0. Our initial velocity in the horizontal axis, here's where the 10 meters per second comes in. That's how fast it was going. It's 10. And then we have our time down here, 2.47 seconds. Okay, so that's that part. And then in this case, we have 1/2 times the acceleration. But we said the acceleration in the horizontal axis is 0. This thing's not going to speed up. It's not going to slow down. There's no forces to make it speed up or slow down. So there's no acceleration in the horizontal axis. I get a lot of people that put in 9.8 here. But remember, that is only true for the vertical axis. That has nothing to do. Gravity always points straight down. It has nothing to do with the horizontal axis. So our acceleration is 0, and then we could put in 2.47 squared here. But since we were multiplying by 0, we know all of that is going to cancel out. And basically all we get is that x equals 10 times 2.47 seconds. The distance that the object goes is going to be equal to the initial velocity multiplied by that time that you got from your vertical axis. And so in this case, you get 24.7 meters. That's how far that bus would go. So when you're setting up projectile motion problems, set up each axis independently and think about the measurements that go in there. And again, the only thing that can be used in both equations on both sides is the time. One more thing I want to talk about in Unit 4 is terminal velocity. So we've got a guy falling, downward. And here we're going to look at air resistance. Most of the time we leave air resistance out because it is kind of complicated. It increases the faster you're moving through air, and so to be able to calculate it, you have to use calculus, except when an object is moving at what we call terminal velocity. Because we know there's a force, we draw a force diagram for this guy, where there's a force of gravity pointed straight down. And of course we can find that by taking the object's mass times the acceleration due to gravity, 9.8. Well, as this guy falls faster and faster and faster, there will be more and more air resistance on it. Now if he's not moving very fast, we can consider that air resistance to be negligible and we ignore it. But as he speeds up, that starts to be not a great assumption, because he's going to be moving fast enough that the air resistance is going to become significant. And the faster he moves, the bigger that air resistance is. And it's going to grow and grow and grow until the point where it equals out with his gravitational force. Because at this point, when those two things are equal, since we know one of these is going to be in the negative direction and one of these is going to be in the positive direction, if they have the same value, then the net force is going to be 0. And if the net force is 0, it can't accelerate anymore. And if it can't accelerate anymore, you can't go any faster. And if you can't go any faster, there can't be any more air resistance on it. So terminal velocity is just simply the point where the gravitational force and the air resistance, the drag, are equal to each other. So calculate this as m times g, and because we know he's moving at terminal velocity, he's moving at a constant rate, and the acceleration is 0, the net force is 0, and so this one up here has to be m times g as well. Look at the equations that we used in Unit 4. Unit 4 was all about gravity. So we got 3 equations. This one, and this one. So the first one, Fg equals big G times m1 times m2 divided by d squared. This equation is used to find the force of gravity between any two objects. Now there's a couple things that you need to know to find that force. You need to know the mass of each object, so that's what m1 and m2 are. And it doesn't matter which mass you put in there because you're just multiplying them. So as far as the order of masses, it doesn't really make a difference. But you also need to know how far apart their centers are, because this distance here is based on how far apart the object's centers are. Now some objects are small enough that we don't really have to worry about are we measuring to the center or not. So if you're going to find the gravitational force between like a baseball and a football, there's not much of a difference between how far apart they are and how far apart their centers are. But when you're talking about planets, there is a huge difference between measuring to the edge of the planet and measuring to the center. So we do need to keep in mind that this really has to be the distance between their centers. And forget that in that equation, that distance is squared. I see a lot of people getting this wrong because they just divide by the distance. You have to square the distance first and then divide. The other thing here is big G. Big G is the universal gravitation constant. It has a value of 6.67 e to the negative 11th, and that's newtons times meters squared per kilogram squared. Okay, I get a lot of people that get mixed up and they think that this is some sort of equation and they're trying to put forces and all kind of stuff in there. But these are not symbols, they're units. They go along with to give us the value of this 6.67. 6.67 times 10 to the negative 11th what? Newtons times meters squared per kilogram squared. It has those crazy units so that it works out with units of the other measurements for mass and distance. This is the universal gravitation constant. It works everywhere in the universe. And that will be listed on the back of your equation sheet. The next equation, get rid of this stuff, is W equals m times g. This is the shortcut equation for finding the weight or the force of gravity for an object here on Earth. Because you need to realize weight and force of gravity mean the same thing. So you can write here, Fg equals lowercase w for weight. Force of gravity and weight are the exact same measurement. They're just two names for the same thing, like car and automobile. Okay? So in this equation, we want to find the weight of an object. We multiply its mass times little g, which is the acceleration due to gravity. Now this is a shortcut. We could use this big equation down here to find the force of gravity between an object and the Earth, but you're going to have to know what the radius of the Earth is and the mass of the Earth. That can be kind of a big equation to do all the time. And so we have this shortcut. We know that all objects have an acceleration of 9.8 meters per second here on Earth. So if we want to know the weight, we can actually just take the mass and multiply by 9.8. But it only works here on Earth. This value right here is the acceleration due to gravity on Earth. And you can use this same equation on the Moon or on Mars or something like that, but g is going to have a different value then. G will have a value on the Moon of about 9.8 divided by 6, about 6 times less. So you can use the same shortcut equation, but you would have to know what that value is. Because most of the things that we look at operate here on Earth, we are going to use that most of the times just to find the weight if we know the mass and the acceleration due to gravity. Our last equation, v squared equals g, big G, times m divided by r. This is the equation to find orbital velocity. It can only be used to find the velocity of a satellite. I've seen people try to use this to find the velocity of a car driving down the road, and it doesn't make any sense. You need to know what the equations are for and where they can be used. The only place that this equation can be used is for finding how fast an object has to go to stay in orbit around a planet or a moon or something like that. In this equation, we have 1m. Now, of course, m stands for mass, but don't get confused. Remember that these objects that are in orbit are free-falling. Their actual mass doesn't matter. What matters is the mass of the planet or the moon that is being orbited. So this is the mass of the object being orbited. So if they give you the mass of the satellite or the astronaut or whatever is going around, or if you're looking at a moon going around a planet, the mass of the moon or the satellite or the astronaut, it doesn't matter. Those things are in free fall, and they'll all accelerate the exact same way no matter what their mass is. But the bigger the planet, the more massive the planet that's being orbited, the more gravitational pull there is and the more velocity you're going to need. G, just like in our first equation, is the universal gravitation constant. So we use that again. That's the 6.67 e to the negative 11th newtons times meters squared per kilogram squared. And then we have r. R is the radius of the orbit. So if you think about it, you've got this planet right here, and you've got this moon or satellite or something going around. It has to be the radius of the orbit. Well, that's going to be this right here. All that really is the distance between the center of the planet and the object that's doing the orbiting, that is the satellite. So really, we can just use the distance between the planet and the moon, or the planet and then the space shuttle or whatever, as our radius. But technically, it stands for radius of the orbit. Other thing to remember, in this equation, it's v squared equals this stuff. So if you're going to solve for orbital velocity, you first multiply big G times m, divide by r, but that is not where you stop. You then have to take the square root of each side to cancel out that squared part right there and actually get the velocity. One more reminder, this equation is only used to find the orbital velocity of something that is a satellite.